So yeah, I'm Alejandro. I'm really excited to be here and to share all the things that I learned on the last few months with you. You can find me on Twitter and GitHub under that handle. Please note that the first O is a 0. And you can also find in that link below all the resources that I use and the slides for this presentation. Before we continue, I wanted to talk about why I think you should care about this topic. I believe that being able to understand what optimizations takes place on your JavaScript programs gives you a unique perspective when measuring performance. So I started my path. By the way, that's me. If you cannot recognize me, it's probably the hair. I started my path going through the history of JavaScript engines and found an inflection point around 2006. Before that time, JavaScript engines were fairly straightforward. They would take the source code and would transform it to an abstract syntax tree, or AST for short. An abstract syntax tree, as you all saw earlier, it's something that omits comments, spaces, curly braces, parentheses, all the things that are part of the syntax and represent expressions and blocks as nodes in a tree structure. After that, the engine would take the syntax tree and would transform it to bytecode, which is an intermediate representation. Bytecode can be described as a well-defined set of instructions and can also be considered as a portable representation, since the operations will not change through different CPU architectures. Machine code, on the other hand, or native code, is architecture-specific, meaning that for the same lines of JavaScript, its machine code will vary from a desktop CPU to a mobile CPU. The final step needed for running the program is what I call here on the top right an execution phase. And it's often described as a really big switch statement that for each instruction, it will jump to the portion of code that implements its logic. Like in most high-level programming languages, JavaScript will not deal with memory allocations explicitly. You can create objects, and all those objects will be allocated internally by the engine. These objects can also be in references, and in order to reuse those precious bytes of memory, you will need a garbage collector. Now, there are different strategies to implement garbage collection systems, but let's leave that for later. Turns out this setup, a straightforward interpreter, is considerably slow, where slow means comparing its performance to a program written in C or C++ after all the optimizations are applied. So a group of brilliant people worked on improvements over this architecture in the 70s for Fortran and in the 80s for Smalltalk and self runtimes. And they came up with this concept of adaptive optimization. The idea is to identify the pieces of your program that are running too often, or also called hot functions, and to compile them in runtime. Hence, the name just-in-time compiler, or JIT compiler for short. After compilation, the engine wouldn't have any overhead for the execution of those functions. Well, with just the interpreter, the functions will have to be interpreted from bytecode each time they are executed. This approach is also a great opportunity to apply optimistic optimizations in the dynamic languages like JavaScript. For example, collecting information about the context of a function call could open the possibilities for type specializing optimizations. So JavaScript engines try to optimize two big things: object allocation and property access. For object allocation, we have what is called hidden classes, which are useful for the engine to know that some objects share similar structure so they can create them faster and have a smaller memory footprint. For optimizing property access, we have inline caches, or ICs for short. Inline caches are a way to save a fast path. So each time, the first time the engine accesses the property, it will use the slow path. But it will record each step needed to get it. Global variables, variables from closures, and also prototype chains could be optimized by inline caches. Let's say we have a 100 objects length prototype chain, and you're accessing something that will need to get to the last one. After optimization, those could have a constant time in runtime. And that's huge. And that's the performance boost you could get by only using inline caches. So be aware that some features of JavaScript will inhibit type specializing optimizations, like the eval function, the with operator, or try-catch blocks. So the basis for most engines implementations consist of an interpreter with two additional compilers. On your left, the one that optimizes compilation time, and on the bottom right, the one that optimizes execution time. The one optimizing execution time will highly depend on information gathered from the rest of the system, and it's also called type specializing compiler. The unoptimizing compiler generally creates inline caches and helps collect type information. Also, the generated code by that compiler, in most cases, will not use CPU registers for variables, unlike the case for the optimizing compiler. Also, type changes in the code could trigger the type specializing compiler to recompile, and in some cases, after an excessive amount of type changes, it will eventually desist and decide to penalize the function, marking it as non-optimizable. Let's switch to a real-world architecture. So SpiderMonkey, the engine that powers Firefox, is not too far from the previous example. On the top, we have an interpreter, which inside it's the parsing phase and what I called before the execution phase. And you have two additional compilers. It will initially transform your code to bytecode and will execute it without any compilation. After a certain amount of times a function is executed, the system will mark the function as candidate for optimization. The baseline compiler will receive the bytecode, plus any other information that the interpreter could gather, and will compile as fast as possible to machine code. If the number of times the function is executed passes a second threshold, then the system will mark as candidate for really, really good optimization, and that's when IOMonkey kicks in. And with the bytecode plus the type information gathered, it will compile to machine code again. Unlike the previous case where both compilers would bail out to the interpreter, in this case, the code will bail out only to the baseline sheet. That is one of the key points of adaptive optimization. Being able to de-optimize is what makes applying aggressive optimization safe. For example, for debugging, you actually want to run the actual source code. Chakra, the engine that powers Edge, shares a similar architecture. It has an interpreter, a non-optimizing compiler, simple sheet, and an optimizing compiler on the bottom right. The interesting part about Chakra is that it can fire additional threads to compile or to run the garbage collector. Say you're running the engine in a 4-core CPU. In theory, you could take advantage of that and compile your code in 3 different cores, or run the garbage collector in 3 different cores, or a mix of both. Both Chakra and SpiderMonkey are currently working on their interfaces to run on top of Node or on bottom. In the case of SpiderMonkey, it's called EmpireNode. In Chakra, it's called Node Chakra. That being said, hold your benchmarking horses. Sheet compilation is not yet enabled on Linux or OS X machines for Chakra, but I know it's on their roadmap. In the case of V8, it has recently switched to a 4-tiered architecture. It has an interpreter on top, a non-optimizing compiler on the bottom left, and 2 optimizing compilers, Crankshaft and Turbofan. The full Cochin compiler resembles the SpiderMonkey baseline compiler. Both will create inline caches. If V8 profiler identifies that a function is taking a good proportion of the execution time, it will then notify the engine to optimize it. Both Crankshaft and Turbofan optimize code with type information. They are competing, but they have different internal representations. Turbofan, it's based on a sea of node internal representation, while Crankshaft used hydrogen and lithium, a high-level and low-level internal representations, respectively. The idea, I know, is to deprecate Crankshaft eventually, and also full Cochin compiler. In the case of Crankshaft, they also want to migrate all their optimizations to Turbofan. I know on Node B7, the performance for array cloning or getting the sum of an array, it's very stable, unlike any other versions of Node like B4 or B6. You will have to enable Turbo with a flag in Node. So Javascriptcore is the engine that powers Safari and has also a 4-tiered architecture. It has an interpreter on the left, on the center a non-optimizing compiler, and 2 optimizing compilers, DFG and FTL. Sorry. The low-level interpreter and the baseline compiler both use inline caches. So the engine will try to apply heuristics to know which level of optimization is needed. And interestingly enough, at any point, the stack could have entries of generated code for all 4 tiers. You can see there's a component inside FTL, which is LLVM. LLVM is an open source project that applies aggressive optimizations and have all sorts of uses outside JavaScriptcore, like in ECMAScripting. It's being used to compile C to JavaScript. The engine will gather type information, the bytecode, and will transform that into a lower-level internal representation to fit that into LLVM. I know they recently switched to a new backend for the FTL called B3 in order to keep the optimizations they wanted, but reduce the compilation time. But that's only on OS X machines. So we just briefly talked about the most advanced JavaScript engines. Let's try talk about the optimizations, some of the optimizations that they apply. Let's say you have a loop executed many times, and inside its body, we have an expression of just something, adding the variable where incremented, multiplying by some arbitrary number. One would say that the reasonable performance improvement would be to make the calculation once and reference it through a temporary variable in all the iterations, especially if it's not changing in all the iterations. All the engines mentioned here are applying this type of optimization, and it's called loop invariant code motion. One of the simplest optimizations Sheet compiler could apply is function inlining. Say you have, again, the for loop, and inside its body, we execute a function, right? If the loop iterates a certain amount of times, the profiler will identify the function as hot, and if some conditions apply, will copy its body and will paste it directly inside the for loop. Now, those conditions are generally in terms of the size of the function. If it's too big, will not get copied. Now, you might be wondering why it should be faster since it's the same code. In low-level programming languages like assembly, calling a function would end up in a context switch. Right after the execution of the function, we'll have to save the status. And after, before returning from the function, we'll have to resume the previous context too. Let's continue with the next optimization. Imagine we have the loop again with just an expression, right? In this case, it's a sum. It could be any expression you want, but as long as it doesn't have any side effect, like assigning the result to a variable, doing some calculations with that expression, calling a function, returning that expression, anything that have a side effect. And it could be avoided, but just doing anything at all, if you are not using it in your code. And that's what the compiler will do. Just remove the expression. This optimization is dead code. It's called dead code elimination. And some compilers, like the hotspot JVM, would even go further and delete the whole loop. So we mentioned before there are different strategies to implement different garbage collection systems. Here you can see a brief comparison of them. We'll talk about how they are implementing its different engines. Generational garbage collectors will group objects by their lifespan and will assume that young objects are more likely to die than old objects. Under this strategy, the new objects will be created under a tenor space, a nursery space, and promote long-lived objects to a tenor space. So incremental GCs will interleave their work with the work from the main program, in theory, producing shorter pauses. On the contrary, a stop-the-world strategy will halt the execution of the main program until a full collection of the heap is done. And that's generally on the order of the heap size. GCs can also be described as precise or conservative ones. Precise GCs can identify all the references, and conservative ones look at memory patterns in the heap to identify references. This last approach could also lead to false positives, but it's not always a problem in practice. So in this link, you can find all the resources, again, that I use while working on this presentation. If you want to read more about Sheet compilers or garbage collection, if you're interested in the details, there's a lot of material in there. I'm working on a way to detect on runtime which optimizations are enabled, and so far had some good results. You can distinguish those ones who are using that code elimination, hidden classes, loop invariant code motion. So a question on JavaScript engines, a good question would be, how do you measure their performance, right? And it's not an easy answer. Out there, there are a lot of benchmarks by these major browser vendors that test all the edge cases of their optimizations. But certainly, micro benchmarks doing measurements for small operations or for different loop constructs will not show you the whole picture. That being said, I think we can aim for maintainable and clean code without sacrificing performance. All the optimizations that I came across had reasonable requirements to apply, like for functions to be monomorphic and things that had to do with dynamic typing and had nothing to do with obscure features of the language. That's all. Thank you.